Pluto, the baffling bantam planet living at the external ranges of our planetary group, is working up fervor inside the galactic local area. Later reports indicate a potential experience with Neptune, raising worries among researchers and space aficionados alike. Eminent specialists, including Neil deGrasse Tyson and Michio Kaku, have sounded alerts about the expected results of this heavenly conflict. Yet how did Pluto end up in this framework in spite of these complicated powers? Significant astrophysicists are expressing worries about a likely crash between Pluto and Neptune. This raises inquiries concerning why such a crash, which appears to be far-fetched given these complex elements, is currently a subject of concern. Neil deGrasse Tyson, a notable astrophysicist, offers an extraordinary perspective on the secrets of our solar system, especially in regards to Pluto. Tyson, popular for renaming Pluto as a bantam planet rather than an undeniable planet, shares sagacious thoughts on how our understanding of heavenly mechanics is continuously advancing. Tyson sees Pluto's renaming not as a downgrade, but rather as an important acclamation to our expanding knowledge about the various objects orbiting the Sun. His approach to divine mechanics involves persistent learning and adaptation. He sees the intricacies of orbits like Pluto's as a sign of how much more there is to discover in space. Tyson believes that the appeal of these questions is what makes space science so dazzling. Moreover, Tyson is aware of how space-related events and discoveries influence public interest in cosmology. He thinks events like Pluto's renaming and its surprising orbit are potential opportunities to capture the public's imagination and interest in the universe. By examining the dynamic and sometimes irrational aspects of space mechanics, Tyson aims to encourage a deeper understanding and appreciation of the universe. Neil deGrasse Tyson opens a window for the general public to wonder at the miracles and secrets of the universe. Working alongside other researchers, Tyson actively alerts the public about the likely risks of Pluto's eccentric path. After a broad investigation of Pluto, he has raised concerns that the three-body issue could pose a real danger, suggesting that a collision with Neptune is extremely overdue. Moreover, Tyson stresses how such an impact could disrupt the equilibrium of the universe and lead to disastrous results extending to Earth. A collision between Pluto and Neptune would be an uncommon and disastrous event in our planetary group. This crash would release a huge amount of energy, potentially breaking apart Pluto due to its smaller size and icy composition. Debris from the impact could disperse across the nearby planetary group, presenting potential risks for other planets and their moons. For Neptune, such an effect could possibly alter its atmosphere and orbit, depending on the specific details of the impact. Michio Kaku, a notable theoretical physicist recognized for his work in string theory and science communication, offers an exceptional viewpoint on this situation. His perspectives on the future of space exploration and the relationship between divine mechanics and theoretical physics provide profound insights into phenomena like Pluto's orbit. Kaku sees the study of Pluto and its orbit as a glimpse into the future of space exploration. Understanding the complex gravitational interactions and orbital elements of divine bodies like Pluto, according to Kaku, can offer crucial insights for future space missions. This knowledge can aid in navigating the solar system more effectively, anticipating potential hazards, and planning missions to the outer reaches of our planetary group and beyond. Kaku emphasizes that the lessons learned from studying Pluto's orbit can be applied to explore other celestial bodies, providing a framework for approaching and understanding distant worlds. In examining the physics of planets, Kaku frequently highlights the deep connection between divine mechanics and theoretical physics. He believes that the movements and interactions of planets, like the gravitational dance between Pluto and Neptune, are not isolated events but are connected to fundamental principles of physics. Kaku's work in theoretical physics, particularly in string theory, aims to understand these principles at the most fundamental level. He proposes that considering the intricacies of divine mechanics, like Pluto's orbit, can yield insights into the underlying laws of the universe. Like Tyson, Kaku has also addressed the potential impact, relating it to his theories about the universe. If Pluto and Neptune were to collide, it would be a significant event in astronomy, offering an exceptional observational opportunity that could potentially contribute to our understanding of string theory. String theory, a theoretical framework replacing point-like particles with one-dimensional strings, seeks to describe the fundamental forces and matter in the universe. The impact of such a scale in the solar system could create extreme conditions of energy and gravity, providing insights into the behavior of fundamental particles and forces under extreme circumstances, a key focus in string theory. Additionally, the gravitational waves created by the impact could provide valuable data for testing predictions of string theory related to gravity and spacetime. While the immediate impact on Earth would be negligible due to our distance from the outer planetary group, the scientific implications of such an event could be significant, potentially enhancing our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's orbit serves as a striking example of heavenly mechanics, displaying both stability and chaos within our planetary group. The unique qualities of its orbit, influenced by the gravitational forces of neighboring planets, especially Neptune, highlight the complex and dynamic nature of space. The universe holds many secrets, and the three-body issue is just one of them. There are other potential disasters that researchers anticipate. While the chances of planets crashing into each other in space are very low, it is not entirely impossible. The way planets' orbits are affected by various factors, including gravitational interactions, is explained by the three-body issue. In some space systems, like TRAPPIST-1 with 7 Earth-sized planets, gravitational forces create a rhythmic pattern called orbital resonances. These patterns can make planetary orbits less stable, potentially leading to collisions. Despite the crowded nature of systems like TRAPPIST-1, impacts are not currently occurring. Researchers closely monitor these systems to understand how planets affect each other's orbits, especially when they are close to each other. This information helps us understand planetary movements in space. Rogue planets, drifting through space without orbiting a star, add an extra unpredictable element. These planets, previously part of a star system, are expelled due to gravitational disturbances or other cosmic events, such as the nearby passage of another star or dynamic instability in other systems. Over time, these wandering planets can traverse vast distances, potentially reaching regions far from their origin. During their solitary journey, there is a possibility of them intersecting with other star systems. If one of these rogue planets enters another nearby planetary group, there is a slight chance of a collision with a planet in that system. However, given the vast and predominantly empty nature of space, the probability of a rogue planet directly impacting another planet is extremely low. On an impact course with its distant neighbor, what could this astronomical collision mean for us here on Earth? Let's explore this unfolding event. Once considered a major planet, Pluto was subsequently renamed as a dwarf planet due to its unusual orbit. Despite this change, it continues to captivate and engage astronomers. Recent forecasts from prominent researchers highlight a concerning proximity between Pluto's orbit and that of Neptune. These experts warn of a potential collision between the two planets, posing a significant threat to Earth. Pluto's orbit around the Sun is marked by its distinctive features within our solar system. Its orbit spans a broad 248 years, and since its discovery in 1930, Pluto has yet to complete a full orbit. Adding to its intrigue is the highly elliptical shape of its orbit, a deviation from the nearly circular orbits of the major planets. Additionally, Pluto's orbit is inclined at 17 degrees to the ecliptic plane, making its path more extreme compared to other planets. One striking aspect of Pluto's orbit is its intersection with Neptune's path for about 20 years in each orbit. During these times, Pluto ventures closer to the Sun than Neptune, defying expectations based on their respective positions in the solar system. So why hasn't a collision occurred between Pluto and Neptune? The explanation lies in the gravitational effects exerted by other planets. The study of Pluto's orbit began shortly after its discovery, presenting a fascinating challenge for astronomers. Unlike most planets, whose orbits lie relatively close to the ecliptic plane, Pluto's unique features include a steep inclination and an elliptical shape. The mystery grew with the realization that Pluto's orbit crosses that of Neptune. The stability of Pluto's orbit amidst these complexities serves as evidence of the intricate nature of space mechanics. The three-body problem in space involves understanding the movement and gravitational interactions among three celestial bodies, such as Pluto, Neptune, and the Sun. This problem explains the complex interplay of their orbits and gravitational forces. Terms like asylum libration, scope libration, and VZK swaying contribute to unraveling this cosmic puzzle. Astrophysicists assert that athel libration, responsible for maintaining planets in their orbits, plays a crucial role in the context of Pluto and Neptune. This term indicates that when Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune, essentially preventing potential collisions. Scope libration ensures that when Pluto approaches Neptune or other giant planets, it is arranged primarily above their orbital plane, providing an extra layer of protection against collisions. The VZK swaying explains why Pluto's orbit around the Sun appears unusual yet remains smooth over time, despite apparent randomness in space. Mathematical simulations in the late 1980s revealed that despite its stable properties, Pluto's orbit is indeed chaotic, with minor initial deviations leading to significant differences over millions of years. Nevertheless, Pluto's unusual orbit maintains stability over extraordinarily long timescales, keeping chaos at bay. Recent computer simulations have improved our understanding of how giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune's unique relationship with Pluto, completing 3 orbits for every 2 of Pluto's, contributes to the stability of Pluto's orbit. Additionally, Jupiter's massive gravity exerts a significant influence, while Saturn's impact, though smaller, also plays a role. Through comprehensive studies, researchers have demonstrated that the combined effects of Neptune, Jupiter, and Saturn ensure the safe and stable movement of Pluto in space for billions of years. These phenomena are crucial for maintaining the order and consistency of cosmic movements in the universe. Without these mechanisms, the solar system would be prone to greater instability and unpredictability, potentially leading to collisions or disruptions from stable orbits and causing cascading effects on other celestial bodies. Understanding Pluto's orbit is particularly critical amidst discussions of a potential future collision with Neptune. This information provides a clearer insight into the dynamic nature of the solar system. Pluto's case highlights how seemingly unstable orbits can achieve stability through the complex interplay of gravitational forces and orbital mechanics. Continuous observation and study of these phenomena are essential for gaining a better grasp of our position in the universe. Exploring the depths of space often reveals the unpredictable nature of celestial bodies, and Pluto's orbit serves as a prime example of this unpredictability. The nature of orbital chaos vividly illustrates the sensitive dependence of a celestial body's path on its initial conditions, as demonstrated in Pluto's case. Even slight variations in the dwarf planet's position or speed can significantly alter its long-term orbit. Computational simulations have been instrumental in helping scientists understand how Pluto moves in space. By making minor adjustments in these simulations, astronomers can observe how small changes can have substantial effects on Pluto's trajectory. In the late 1980s, these simulations uncovered an intriguing aspect of Pluto's orbit. Despite features like AIML and scope libration contributing to its stability, Pluto's orbit can still exhibit unpredictability. Even a slight initial difference in Pluto's position or speed can lead to significant changes in its path over many years. Despite this inherent chaos, Pluto's orbit remains stable over an exceptionally long time, extending over billions of years. This suggests that beneath its seemingly erratic appearance, Pluto's journey around the Sun follows an organized pattern, anticipating vast events. Particularly with planets like Pluto, which have unusual orbits, making long-term predictions is challenging. The intrinsic unpredictability of these systems renders long-term forecasts uncertain. Mathematical simulations help us understand and predict the future paths of celestial bodies, but they also reveal the limits of our predictive abilities. These models heavily rely on accurate initial conditions and replicate complex interactions. Even a small error can lead to significantly different outcomes, making precise forecasts difficult. The turbulent nature of celestial orbits, such as Pluto's, reminds us of the ever-changing universe. While we have made progress in understanding space, Pluto's case highlights our ongoing limited knowledge. The vastness of interstellar distances and the rarity of planets in open space act as barriers to frequent collisions. Moreover, Rogue planets are relatively rare compared to the number of stars and planets in stable orbits, making such events even more unlikely. Understanding the gravitational effects of giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It demonstrates how the presence and position of each planet can influence the stability and trajectory of other bodies in the system.